Hello, and welcome to my next presentation, which is about projectile motion. This is my initial presentation on projectile motion. There will be a further presentation coming up soon. I'm Bernard Taylor, and this is Fez Physics, so let's get moving. These drawings showing the trajectory of projectiles don't seem quite right by modern standards. And it would be interesting to explore Aristotle's ideas and how these ideas were subverted by Galileo and others, but we need to move on. Now, here on the right, I am holding a ruler lightly at the pivot point. I tap the ruler in the direction of the arrow with my right hand, with my finger. And I usually ask students which coin will hit the ground first. Coin A drops vertically, coin B is projected sideways. And yes, both hit the ground at the same time. The strobe photograph shows a similar experiment with a cunning release mechanism. Both objects, both coins, accelerate vertically downwards at the same rate, but the horizontally projected object has a constant horizontal velocity. We treat the vertical and horizontal motion separately, and we also ignore air resistance at A level and IB level. Right, let's move on. But try this experiment at home. It's easily done. Now, here we've got, I'm just looking for my laser pointer. Here we've got an object that is projected horizontally with a horizontal velocity, ux, of 2 meters per second. So let's explore that motion. Vertically, one of the equations of motion, s equals ut plus a half at squared. Let's just, for the sake of the ease of the maths, take a as being 10 meters per second squared. Vertically, the initial vertical velocity is 0. So s, the vertical displacement, s, equals a half 10 times t squared. Right, that simplifies to s equals 5t squared, or the y displacement equals 5t squared. Now, horizontally, there's no acceleration, no deceleration, because there's no air resistance. So that horizontal velocity is distance over time. S, the horizontal displacement, equals ux times t. So I've highlighted these two equations. Now, let's look at the table. When t is 1 second, then the vertical displacement, y equals 5. T squared is just 1 squared, so y is 5. Horizontally, the displacement is just 2. That's the initial, the constant horizontal velocity times 1, so that's 2. After 2 seconds, well, the vertical displacement, y equals 5 times 2 squared, which is 4. Overall, that gives 20 meters. Now, you might like to try to complete this table, perhaps print it out and try it for yourself, and plot a graph like this showing the x and y displacements. Okay, well, I've done it for you. This is the graph of the horizontal displacement x plotted against the vertical displacement y for this object given an initial horizontal velocity of 2 meters per second and falling freely under gravity. And yes, it does seem to be a parabolic trajectory. Let's look at a few questions. Question 1 here. And just before we start, let me remind you that we ignore air resistance. So we've got an aeroplane being used to deliver supplies after a disaster, perhaps a famine. The plane is traveling at a horizontal speed of 70 meters per second at a constant height of 60 meters above the ground and dropping a package consisting of sacks of rice. We're asked to draw the path of the package on the diagram, in other words, to draw the trajectory, and then to calculate the time taken for the package to fall vertically and reach the ground. Well, drawing the trajectory, it's going to look something like that. That's easy for perhaps 1 mark. But the time taken for the package to fall vertically, we consider the vertical motion, and vertically the initial velocity is 0. I'm using s equals ut plus a half at squared. The vertical distance fallen would be 60 meters, a half, 9.81 times t squared. So t squared would be 2 times 60 over 9.81, which would be 3.5 seconds. Now we're asked to calculate the horizontal distance traveled by the package from the moment of release to the point where it hits the ground, the range, if you like. Horizontally, the speed remains constant. So speed is distance over time, distance is speed times time. We know the speed is 70 meters per second. We now know the time, and we do a simple bit of maths and we get that the distance is 245 meters. Another question. A cricket ball is thrown out of an open window. Well, yes, it would have to be an open window, wouldn't it? Which is 20 meters above the ground. The ball is thrown horizontally at 4 meters per second. Drawn a little diagram. How long does the ball take to reach the ground? Again, we consider the vertical motion. S equals ut plus a half at squared. The initial vertical velocity is 0. So this term is 0. 20 equals 0 plus a half gt squared. We do the maths and we find that t is 2.02 seconds, and let's call that 2 seconds. Calculate the horizontal distance from the bottom of the building to the point where the ball hits the ground. Well, horizontal motion, the horizontal velocity remains constant. Speed is distance over time, distance equals speed times time. 4 times the time, 8.1 meters. So I hope you're getting the idea behind these kind of questions, but of course it does get more complex. Now, my model ski slope here. What is the model ski slope? Well, typically the way I would work this is that this would be a piece of plastic tracking glued to perhaps a wooden base, put on the edge of a bench, edge of a lab bench, 1.3 meters above the ground. And note my points A, B, and C. And we're going to release a marble or a ball bearing from this point A, which is 0.2 meters above here. So we want to first work out what the horizontal speed of the skier is at B. Kinetic energy gained equals potential energy lost, half mv squared equals mgh. Yeah, m's cancel, v squared equals 2gh. And v is 5.05 meters per second. Okay, now just remember that height here, 1.3 meters. We want to use vertical motion now to find the time taken to fall 1.3 meters. Again, s equals ut plus a half at squared. Vertically, from B, that initial vertical velocity is 0. So 1.3 equals 0 plus a half times g times t squared. And we find that the time of flight is 0.52 seconds. Now, we want to consider horizontal motion to find the predicted range, r. Again, distance equals speed times time, so that range equals the velocity times the time. And we worked out the velocity as being 5.05 meters per second. This is the time, and we get a range of 2.63 meters. Okay, job done. But if you were doing this, you'd now actually roll your marble down the ski slope and find what that range is. Incidentally, an easy way to do this and to mark the position of the point where the marble hits the floor is to use a tray full of sand and to measure the distance from the edge of the bench, or the point directly below the edge of the bench. Now, the model ski slope can be a core practical, and the purpose of this is to compare the predicted range with the actual range when the marble is released from 6 different points on the ski slope. Okay, you're expected to plot a graph of the predicted range against the actual range and to comment on the results. You might like to think about this. You should, of course, consider an average value for the actual range. You should consider an uncertainty in the actual range and to record your measurements carefully in a table. And this is an interesting experiment which enables you to get to grips with projectile motion. Now, just before we do finish, I've got a challenge for you. Here's our marble, here's our model ski slope. It's released, and then it leaves the bench at point B and follows this trajectory through the air. We've got 2 heights, H1 and H2. This is the range R. And my challenge to you is that, can you prove that the range R is given by this equation? Give it a go. So let's sum things up. We ignore air resistance in calculations, but we would be expected to know that if we did have air resistance acting, then this would provide a force which would reduce the horizontal velocity and therefore the range. We can't just say in an answer, something about just the phrase air resistance. We've got to explain. And we'll come on to this point in my second presentation on projectile motion. Okay, we treat horizontal velocity and vertical velocity independently. And because of the first point, the horizontal velocity is constant. Now, we hardly need say, but the vertical velocity changes because of the acceleration due to gravity. So, this is Fez Physics. I'm Bernard Taylor, and stay tuned for my next Fez Physics video, when we'll again be looking at projectile motion. We'll be looking at some more complex aspects of projectile motion. So, thank you very much and keep working.